because I can't remember anymore what this is. So it says about the foundation is the lowest division of the engineering structure. Actually, that's the one which is in contact now with the ground, the foundation, which is basically either the bedrock or soil. Here you can see that, for instance, there's a big load structure here, a skyscraper, for instance, or a big heavy structure, and that rests on a cap. And then this one actually itself is sitting on piles, right? And this one actually now reaches down to the ground. Why is that? Because when you talk about lower density, obviously when you build on sand, you know what happens with sand, right? It basically sags. It's not simply strong enough to withstand the weight. So basically, that's the reason why you drill these holes in down there. You simply search for strong foundations, layers. For instance, this one is rock layer with high density, which is strong enough then to withstand. Right? That's basically what they do with deep foundation. That's why they actually drill those pillars in there, simply to look for the soil, not actually soil, but mostly it's rock, hard rock, and simply to embed your structure there. So make sure that the load which comes from here all the way down here through the ceiling, then through the column, down to the ground, to the foundation, and then basically into the ground. The natural ground, of course. And of course the earth is big enough. If it's big enough, then it will hold forever. I'm not sure whether you heard about that. I just read the news another day, about a couple of weeks back, about Manhattan in New York. There was some alarm raised that the whole bed on which basically all this skyscraper rock starts to sink because of the enormous weight of all those buildings there. So I just read it the other day, it was in the news, that this one actually starts now because of the enormous weight of all these structures. And look at how densely it's built with skyscraper after skyscraper, and they weigh a lot. And then it starts to push down the entire rock, the entire plateau on which is basically resting upon. So that basically, if you have only one building on a big area like this, and of course it doesn't make difference. But if you have many of those buildings, then of course it does. You can imagine, because it pushes it down, that on those pillars down here on the bottom, there's a lot of pressure. Because that's actually where the whole weight of this rests. So, say the work, the concentrated load into the distributed load underneath. We have two basic foundations, next simply the word. One is simply the deep one, for large structures, tall buildings, an area which is challenging soil conditions. Some areas have problems. Here in Brisbane, I am not entirely sure what the layers underneath, but some areas is granite, for instance, and granite is one of the hardest substances in nature, which means it's very strong. So that's the deep foundation. We will not really be touched by it, because we do not have such deep foundations. And the other one is what they call a shallow foundation, and the word says it. It simply sits on the ground, almost directly on it, or dig it a little bit out, but something like for the house, right? Or parking space, or even, although I do not think about, you do not have any foundations for roads, right? I think you have only those pebbles underneath. I don't know, you have the road design, I didn't. So you have to basically, it sits directly onto the natural ground as it is. Right? It doesn't have to be digging in. Right? So you actually transfer the loads from the buildings directly into the ground without much. And that's normally the surfaces. There could be soil, sand. The sand probably less, but simply any foundation which is strong, soils or ground conditions which suits. Right? It doesn't have to be rock. Because, first of all, the building is not heavy. A house, especially in Queensland, they are simply timber, right? and that basically, and actually that slab is wide, right? Which means the load is actually distributed, which means the pressure generated by that is quite low. So you do not have really that challenging conditions for the ground. So here are some comparison between a shallow and a deep foundation. Of course, for the depths, for instance, when we talk about depths between less than 3 meters, that's what we call, or what they call, I'm not a civil engineer, but what they call a shallow foundation, otherwise it goes down there. And the load transfer, that goes directly into the near surface soil layers. Right? So it is mostly low soil. Right? Right. And for the load transfer, that means simply from the top all the way to the ground, that is actually called basically normally to rock, to rocky stuff, not soil anymore, because when you're deep down 10 meters or so, then there's actually no more soil, there's mostly rock layers. Then the cost, of course, for going down is much higher. When you see the machinery you need actually to get down and how to actually make such a thing, it's much more expensive, right? And of course it takes longer because you have to drill these things, right? And suitable basically for this one. But this point here, that is actually the point why I actually brought it up here, the soil requirement. That means the ground on which it sits, soil or rock, that determines also for the shallow or the deep foundation, right? We need strong soil. Whatever strong means, strong soil condition. And that's actually our part which we do when we have the first whack. Right? Okay. So for the deep foundation, there are two types or several types. Basically, one is the pile, which is simply a thing like this on which it sits on. It's a slender column or long cylinder made of materials such as concrete, steel, or timber. I wouldn't have believed it that they use also timber, a simple timber for the foundation. For here to such a pillar. And in fact, I saw them actually here doing this here as well in Brisbane. Just I live north in Strathpine. They just redesigned the area, and they use some really hard timber. This hard, this timber which you use also for the posts here, for the electricity posts and the telephone poles. They're all made of this hardwood. This stuff is really hard. I mean, if you try to drill a hole into this one, that's actually really challenging. It's really tough. And they use timber for making this. Right. And it's simply because timber is quite resistant to water, quite resistant to corrosive soil, for instance. Right. So that's sometimes why they choose timber. But otherwise, it is normally concrete. Miriam was telling me that she actually did a project in Colombia where they built near the coast, where they also use timber pillar like these ones here, because of the environment, because of the water, especially near the water. The salt water is very bad for concrete and for steel, but for timber, it doesn't really matter. Timber is really, really, really resistant. And you wouldn't believe it if you don't really see and try out how hard that stuff is. It's amazing. This timber here, especially in Australia, this one is amazing. So the pier is a column of a well, and the pier is like this one. This is actually a little bit more stumpy. And it has down here an area which they call a bell, and it simply makes the area underneath bigger. Right? It's simply because just to distribute the load which comes from above over a certain area, which means you reduce the pressure. Right? That's the same thing as you walk over snow, right? I think I mentioned an example last week. When you walk over snow, freshly fallen snow, you will sink in, right? Especially when it's half a meter high. But if you wear snowshoes, which looks like simply like tennis racks on your shin, you can walk over it without barely sinking in. It is because you distribute your pressure, you weight over a certain area, larger area. And that's what you see. End-bearing pillars, that means simply the load which comes on the top here goes straight down to the ground. And basically the load is here down on that. Basically everything here, the whole weight is distributed over the load. Simply what I just said about with the previous example. The entire load of the building above or whatever that's on there is exactly at this. And this area and that rocky area, the soil, must withstand the load from above. That's the only area. And another thing which they call a friction pile is not only that, okay, the entire load from above will be counteracted by friction on the side. Right? It's simply like this one. Right? Like this, right? Because there's friction, right? So that means if I actually apply a load, right, it holds it. Simply by the friction I generated with my hand in contact with this. Why? Otherwise it would slip through, right? If there would be no resistance, it would be smooth, then it would simply. That's why you basically have weak soils. Then they have simply friction files. They simply have something like this here, just to increase the friction. Here is an example on how to make these things, how to actually create such pillars. Right? They simply, and that's a technique which they call CFA, continuous flight auger. That means there's something. This is an auger here. Simply a big drill, right? And it's actually really cool to see those machineries when they really go down. And at the same time, then, when they drill it, then they reseed and then they fill the concrete, plus the reinforcements. Okay. So I think that. And the other one is actually simply hammer it in. So either drill, which means then you have to take the soil out of it, dispose of it. Here, they simply ram it into the ground. Which means, what actually happens is basically that soil which was here is going to be compressed to the side and creates an extra pressure on the pillar. Noisy as hell. For those who have probably lived near a construction site, and you hear that bam, 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 bam. That's really, especially they do this when they build bridges in water. You probably have seen, I'm not sure, when they designed here that the Kowonga Bridge. No, what's the name of this Kurilba Bridge? The pedestrian bridge over the city, over the river. Not this one, but there was another one. Was it Kurilba Bridge? Any of those, it was a long time ago. I think you were not even here at that time. They basically, when they actually need to create a support for the bridge in the water, they use this. They do not use a drill because the water doesn't, they simply hammer it in. Right? And quite amazing. Advantages and disadvantages, I think we can save this because this is not, we need to consider because we do not go into this deep foundation. So here's the material, that's at least something which is interesting. I thought actually first that would be fake AI fake or so. This looks very unnatural, but apparently it's really like a foundation which they use for whatever it is, right? It looks like a fake for me, right? But apparently it's not. Here, that one I showed you, there's another one, that's timber, a timber structure, and this is a concrete. I do not know whether, I don't know where they are. This one, I just took the internet and I was simply looking at different materials, and here's for the timber. But at least you can see it's a mushy looks like a swamp-like environment, right? And especially when you have salt water in that swamp environment, then you use timber. But that's all. This one is much more important for us. We call that the shallow foundation. What I can say about this one, the shallow foundation is a structure sitting on a near It is characterized that its width and length is much larger at its depth. Makes sense. Right? Simply that's what's called a shallow. Right? Again, this is actually quite boring, I know, but I have to tell you that because one part of this brack here and one part of this unit is talking about health and safety. As you can imagine, when you have a shallow foundation, because you have to dig it all out, but only to a certain amount, that is of course much less risky than a deep foundation. You might have heard about those accidents you have when you have deep excavation and small, not deep and shallow excavations. So basically I just have to mention that to you so that you are aware of this, right? So that we know to cover that topic. Right? So it is simply economically and probably the most widely used foundation. The foundation load transfer, that's the first word, load transfer. I mentioned that simply basically from our building to the ground. The transfer into the ground, that's the point. How do we manage that? How do we manage it such that it is reliable, stable? And now you can actually imagine that depends on what they call the soil bearing capacity. That word is the most important one that's dominating basically this module. So each soil, whatever we build on, rock, sand, clay, whatever it is, they have a certain, what they call soil bearing capacity. So please remember that word because that is actually part of your track 1 for this one. So, and this one, and where do we get that information? The soil bearing capacity. And that is actually done by tests. So when you go to the construction site, they always start with a geotechnical report, a geotechnical survey. People actually going there and do something. They drill holes into the ground and get soil samples, just to determine the compositions of the ground you want to build upon. And in the end, to find out what, for instance, the soil bearing capacity is. Okay. Such a test is part of the geotechnical report, which is in the next. So now again, this is basically more clear and more nearer to the project we're going to do, and also with one of those tracks we are going to do. We have basically types of shallow foundations. The first one, and that's probably the most easiest and the simplest one, and that's the one which we also consider in the track. That's what is called a footing. A footing is simply a slab like this on which the column rests. The column we talked about, that's why I've drawn it like this. This is the basic example of a footing. The column sits on that footing. So the footing comes always with this little square or rectangular area. It's very rare that it's round. I think I haven't seen any round things, but this one, and a little stump on top of it. And on this, the beam, the column sits on. Okay. It supports a single column. The other one is a strip or wall footing, and that is simply, for instance, for a house. Right? So you see a wall on this one, and underneath sits directly that slab, which basically follows the wall altogether. Then there's a combined footing in which you have one footing on which you basically share one or more than one column. Right? You can see this one here, compared to this, or compared to this, it is simply more economic. And moreover, this one here has a pressure which is higher, for instance, compared to this, because the area is higher, larger. I see everyone is following, which is okay. So here you see that's one of the old slides, which I simply forgot actually to change the photo time. So this is one where you basically look. I think I need to delete that one actually. That's actually I simply forgot to delete this one. Delete. So now the question is deep or shallow. I do not want to go into the discussions. It is simply depend on where you want to build it, the ground conditions. One of the problems is here water in general. Groundwater you have, salt water when you're close to the water, and in Australia also you have these artesian water basin, which is one of the biggest water areas underneath, right? That's what they call artesian pressure. Right? You know that Australia is probably one of the biggest water reservoirs underground in the world, and also one of the oldest. Right? You know that? The artesian basin. It's basically half of Australia underneath, right? It's water. Right? Artesian basin. If you check it out, then you will find it, right? It's a really big, very ancient water. Right? So you basically look at the soil type. If it's some areas are depending on clay or whatever soil you have. Water table, water content, and of course site vicinities. If you have something like this one here, you are simply confined in space, and you want to build, to dig in. Right? You cannot simply spread out for whatever reason, which means you have to go in. So it depends also on the location. You do not make that choice. That's all what the architects do. Excavations. Again, I do not know why I have to bring this up here, but it is part of this track here, part of this requirement here. So there are also two types. Roughly you can two types. So you actually either you create a big pit, which is simply a big hole, right? Like this one here, large hole with a slope here up there. Right? And the other one is called a trench, where you simply dig narrow but deep, for instance, for pipes. Right? So you actually lay out the. So this is a long and narrow ditch, normally not that deep. It's simply because of geotechnical structures, for instance, like irrigations or what is it actually? What are culverts are made for? What are culverts? We actually did this last term. For drainage, sorry. Yeah, that was the word. Sorry, I'm a bit tired this morning. So drainage, something like this, right? Of course, here, that I have to mention it, health and safety. For a ground, a hole, right? Especially when it's deep, it's very dangerous, of course, you fall in, right? Shown here, right? So when you see those things in the excavation, by law you are required, even if you dig a small hole in your backyard, then you have to put up something like this, such a sign. There's an excavation in process, just to make sure that no one falls in. That actually, when someone actually working, that the soil actually starting to collapse, and so on. And I'm not sure. You probably heard about the story. There was, especially in Germany. It's a story that's actually indeed true. in Germany, there was a person who was, I do not know whether he wanted to create a swimming pool, so he dug out a big excavation in the backyard, on his own property, and fenced everything, right? So he basically dug it out, 2-3 meters deep or so, and then overnight, well, he went into sleep, and then a burglar came over. So he climbed out of the fence, because it was pitch black, and he fell into the ditch. And he sued the owner, and he got compensated. Because the owner did not fully secure the excavation. German laws. I mean, I remember that there was really a big outcry in the news at that time, that this idiot, with the full intention to do harm, fell into the ground, fell into the ditch, got injured, and got compensation because of this. Right? And that's another reason why they actually have now everywhere signs, right? Like, you guys, has someone actually take away coffees? When you go to the segregator, you see actually always on those lid, caution, hot content. And you know why that is? Do you know why? Because some idiot actually got, I think it was McDonald's, I'm not entirely sure, he actually got coffee or tea, hot water of course, I mean it makes sense, and he burned himself. And he sued McDonald's, in America of course. Yeah, of course, where else? I mean, and he got compensated, I think $10 million or something. Because it poured out and he wasn't warned that it was hot. And that's the reason why you have now everywhere those warning signs are, simply to cover their bum. That's the reason why you see always those signs everywhere now, because of the insurance. It's ridiculous. I mean, just imagine. I mean, if I dig a hole, right, then I'm aware that I won't fall in. But you must put up signs. You must make sure that the most stupid user, right, cannot get injured. It's ridiculous, but that's the way it is nowadays. And that's the reason why. It's just, and that's why they have the signs. Right? At some stage it makes sense, especially when you have some sort of a hazardous environment, that you need some, because you might not be aware that, for instance, when you actually work in an excavation, that you might be exposed to airborne contaminants, basically. Contaminant, for instance, when basically people dug in asbestos because it's invisible, or the fine dust, and the fine dust settled in the lung, and you might not be immediately aware of that, right? You wouldn't go out, and you are always exposed to contaminants out there because of the fumes, and the Brisbane is very dusty anyway, right? But so that thing it would make sense, but so this one here, but you are legally required to put up. So these are the possible scenarios which could happen. People would fall in, they could collapse, and be stuck inside by falling. And that's why you have these ones. I'm not sure whether you heard about the word shoring. Right? It is simply something like two plates here, kept together by jacks, kept apart by jacks. They simply use jacks, so they push them apart, so that the soil on the side cannot collapse. Probably have seen that. I'm pretty sure you have seen this somewhere. And here for the big construction site, you see that's quite a big constructional efforts to make, because that soil condition might be too hazardous. Right? So they use what is called shoring. There's also a video up there which I do not want to show you. It simply explains, actually quite good. It's an Australian one. It's actually quite good. And explain a little bit about shoring and what you need to look after. But I think we can skip that because it's not really relevant to our plan. Now we are homing into what we need to do for the first crack. And that is actually I do not know why this has been brought up like this. This is from the original slide owner. I said that we have to find out first, before we actually do any construction, first of all, what is the soil condition? Right? I mean, this is one part of the whole thing, and that's why they do this, what's called surveying. Right? You know, those surveyors with their laser thing there, basically just to make sure that they actually have measured out everything. It's also a legal requirement for the, I don't know, for the councils. Basically, when you build on something that is registered building there at this location, at that height in particular, and so on. I'm not an expert in that at all. And there are two types of surveying, right? Simply because of the scale. Right? And again, I don't know, I fail to see why you put this up here, but for the surveying you have two conditions. One is called simply the plain one. We live on there's no flat earth people here, right? So we live here. Yeah, I just have to mention that because when you look at the, people actually, look, this is actually still amazing to see people that believe in the flat earth. But in fact, the earth is flat on a small scale when you look at this stage, right? So for our sites, what we do, we always consider our area, which we consider as flat, right? Of course. Right? But when you do a little bit more, when you road design, I do not know, larger structures, I do not even know why you probably need this for construction here. They typically consider the Earth as a sphere. That means all those straight lines are in fact curves. I cannot imagine this, except if you want to build from a road from here to Darwin, for instance, right, straight through. Right. There, of course, that makes a difference whether you consider it flat or you have it curved, right? And of course, that makes a difference. So I do not know why they use this one, but here that's actually the purpose of the surveying. So design the land parcel layout. Everyone knows now, for those who looks for houses, what shortage we have, right? So they basically look for these kind of thing to parcel the possible and available area. Making topographic maps, doing road and highway alignment and leveling, and surveying underground mining transportation tunnels. Whatever that means for us. But this is now what we need to consider. The only thing what we really want to know is the soil condition. For us, we want to know what soil we have and how do we quantify that. And that in turn is then be used for the design of the footing. So this one is now really the hard car, where you basically look at the geotechnical report. The geotechnical report is standardized. There is a standard for this one, the 1289, and it says about provide specific information on the surface, subsurface soil, rock and water condition, and used for the pre-design and the design of the construction. So going to be your prac exercise taken from a real life, not real life, yeah, it's probably a real report to extract the soil conditions and the soil capacity at any location. So that's why you do something like that. What you do core sampling here. They drill into this one and take this one. So that actually gives the structural engineers the specific information needed to design the structural foundation. In other words, without the geotechnical report, you can't start. Because if you design a foundation but you have no idea what ground you have, it's built on sand, right? Literally and figuratively. So that's actually why you need to have these, what we call a survey, the geotechnical report. Okay. So these ones here, I'm just leaving it up to you, but it is highly relevant to your quiz. So you will find a lot of information there. When you go to the quiz, the answers are in here. That simply means who are the stakeholders, who wants to do what, and who wants to have something. So if you are the owner, if you are the civil engineer, if you are the contractor, and so on. I do not want to read that because it's actually really not boring. I think you can read it yourself, right? But when you see the when you see in the quiz, it's a question related to that. Exactly with this. I think you can read yourself. I know how boring it was, seeing from the attention span I got, which is okay. I have no problem with that because I know that you guys actually focus on your pracs and whatever you do. Even if you just listen half, that's enough. That's all you need. I try to emphasize the important thing by raising my voice so that you are more aware. I think we have a break now, and then I will go to the real important presentation, and that's the geotechnical report. Right? After, say 10:30.